Hello class, welcome to our adventure online in chapter 4. We're going to be talking about ratio and regression estimation. We will start this chapter with the attention to simple random sampling without replacement. So we're going to go back in time to chapter 2 when we were dealing with simple random samples without replacement, introduce the concept of ratio and regression estimation, and then as we get through the chapter, we'll go back to the stratified sampling scenarios where we will apply the ratio and regression estimation. So before we start, I want to give you some motivation as to why you might want to estimate a proportion or a mean using a ratio estimator instead of the straightforward estimators that we've learned so far. You may actually have an interest in a ratio as the parameter of interest. So for example, if you were talking about the variable y was the household income and the variable x was the number of occupants, and you took the ratio of y to x, you would essentially be calculating what economists say is the per capita income. It's the total household income divided by the total number of occupants, and that is over the entire population. So here we would have estimated y, the total household income, and then we would have estimated x, the total number of occupants per household, and we would have taken their ratio, and that ratio would be what we call the per capita income. So that is one particular quantity that's actually expressed as a ratio, and we actually need to express that as a ratio for it to make sense. Another one would be in the era of the COVID-19, might be sort of exposure rates or vaccination rates. So X is the variable called the total population exposed, Y is the number of vaccinations administered, and the ratio of Y to X is the vaccination rate among those who were exposed. Last one is an example. You wanted to compute the mean average rental price per roommate. This is often done in college towns where people rent not apartments or actual houses, they just rent rooms inside of those quarters. So the monthly rental prices that you see like on Zillow or on rent.com, for example, would refer to the cost of the entire unit being rented. But if you were a student looking for a place, you might care about the cost per renter. So in this case, you would calculate the average rental price per property, and then you would calculate for the X variable the number of roommates or occupants per rented property, take their ratio, and you would get the total rent paid for per renter. So this allows you to express things as a rate. For example, we see a lot of rates in public health. We see a lot of rates in economics. So these are other areas where people do care about expressing things as a rate as opposed to just a single variable. So as you can see, ratio estimation is going to require two variables. One variable for the numerator of the ratio, the other variable for the denominator of the ratio. Let's say, for example, just to give us an example to work with here, you wanted to estimate the mean monthly rental amount paid to landlords by renting students in this class. So we could take a simple random sample of, say, 5 students without replacement, and we could certainly, ask people, what is the amount that you paid to your landlord this month? Now, you could have an apartment by yourself, you could be renting a room, you could be in a house where you have no rent, but in any case, you would report the amount of rent that you paid. We would take the average for those 5 students in our sample, and we would get an estimate of the true parameter, and this estimate would be unbiased based on what we know about simple random samples without replacement and the sample mean estimator. But let's say that we had a second variable at our disposal that was available for the entire population. So where else have we seen variables that are available for the entire population? In stratified sampling. We said that in order to stratify a population, we first had to know the auxiliary or stratification variable on all of the population. It's similar here, only these variables are typically not categorical variables. These might be continuous variables that we have for the entire population. we'll call these our auxiliary variables. And if that variable was positively associated or positively correlated, you could also think of X as an ordinal variable, like education, for example. And so in that case, you'd be looking for an association between the X variable or a correlation between the X variable and the outcome that you care about, the Y variable. So you could create another estimator using this information that might actually be more precise. And the reason why it would be more precise is because we're taking advantage of the correlation between the X variable and the outcome. This is exactly why stratified random samples that stratify on the correct variables, or variables that are really useful, actually partition the between and within sums of squares so that the overall estimator has lower design effects or lower variance. It's exactly the same thing. The estimator, the stratification is actually incorporating the X variable before you sample. Ratio estimation is incorporating useful auxiliary variables after you sample. So this is a point where maybe it's not important to stratify on this X variable because I have other things in my survey that I care about, and if I stratified using those variables, it may actually make the rent variable worse in terms of the estimate. But if I have a second variable in the population, I don't necessarily need to use that in the design to create a better estimator. I can actually use that in the estimation process. So when you think about stratification and auxiliary variables, you've got to be thinking, what's happening as we design the survey? When you think about ratio estimation and auxiliary variables, you have to be thinking, these variables I haven't used in the design, but I can use them in the analysis or in the estimation phase. So that's kind of how I separate them in my mind to keep them straight. So let's talk about this estimator that I've been mentioning. But in order to do that, let's look at a more concrete example here. Let's say that we usually want variables that are positively correlated only because we're assuming a regression through the origin, and it's easier to think about positive correlation, but it can still work with negatively correlated variables. But in this case, let's look at an example where I wanted to estimate the total monthly rent paid per person, and the auxiliary variable that I had available to me was number of roommates. Now clearly, as the number of roommates goes up, your monthly rent, total monthly rent, must also go up in general because you have more roommates. You probably need a bigger apartment. You need a bigger compound, etc. Now this correlation may not be 0.9. It may not even be 0.7. It might be something like 0.55. But in any case, that positive correlation could be enough to make the ratio estimate more efficient than just the regular mean estimate, because I can take advantage of this extra variable. The population correlation coefficient is essentially Pearson's correlation coefficient, except that in this example we see capital letters and X bar U because we're assuming that we have a finite population. So this would be the Pearson correlation coefficient that we would compute if we took the entire census of the population and we collected X variable and Y variable information. Again, we're using these capital S's to refer to the standard deviation in the population for those variables. Now we can define the ratio of population totals or population means of the two variables exactly the same way. These actually are the same because the denominator is just capital N in both cases, and it basically cancels out. So you're either going to be talking about the ratio of totals or the ratio of means, but in any case it gives you the same value. This is B. Now in the regression situation, we would write something like y equals alpha plus beta x plus epsilon, and this beta is the Greek equivalent to what we would be referring to as capital B in the finite population case. Remember, we're not using Greek letters here to denote our parameters, but in this case, this is exactly what this B is trying to estimate. And more precisely, we're assuming that regression is going through the origin, so we're forcing our coefficient here, our intercept, to be 0. So we're really looking at this kind of scenario here. And this beta coefficient is really the B that we're talking about. Now, when we get into regression estimators, we will allow the intercept to be included, and we will allow additional predictors. But for now, the simple case scenario we're working with is this equivalent for the model for the regression approach. So we can estimate the mean monthly rental amount using a weighted estimator. Remember, this S refers to the sample. These are the sampling weights that come from the design, and the numerator variable is one variable that you're looking for. It's the Y variable, and this would be the auxiliary variable. So I know that these are mislabeled. This should actually be a Y. This should be an X if I was to be consistent with this notation. The denominator, the way I remember it, okay, just so that you all remember, is the denominator of the B or B hat is the statistic from the known auxiliary variable. Okay, so that's how I remember what goes in the numerator, what goes in the denominator. Now we can estimate the mean monthly rental amount by the simple sample mean that we've learned already. But we could also create a new estimator based on the ratio. And this would be simply the product of my estimated B times the X bar U, or the estimated B times the, so in this case, forgive me, in this case, the B hat is simply the sample version of these two things, right? So we're going to replace, we don't know Y bar U, so we'll replace it with Y bar from the sample. This is the simple random sample. That's exactly what this value is here. And then the denominator will be the sample mean of the X variable. Now remember, we know the X is for the entire population. So that's where this X bar U comes in. Now, how does this get us back to the Y scale? Let's talk about that for just a second. This this B quantity here is essentially an average unit of Y per average unit of X. So this is telling us that I got on average this many Y's per this many X's on average. If I multiply this by the average number of X's, those X's essentially cancel in terms of their units, and you're back on the Y scale to give you the average units. Now, again, you can also estimate the population total by NY bar U, which we've already seen before. Actually, this is NY bar S. This is actually not U. It should be S from the sample. Or we can, so that's the straightforward version. So this is NY bar S. Or we can use the ratio estimator, which is essentially B hat times the total in the X variable. Now notice the things we're multiplying by are the known quantities from the X variable. If I know the X for everybody in the population, I know the X bar U, and I know the total on the X variable. So let's look at why this would be a total as opposed to a mean. So this beta quantity essentially tells me that this is the total number of Y's per X. And in this case, I have this many X's. So if I multiply the total number of X's by a quantity that gives me a rate of total Y's per total X, then I get total Y. So that's how the math works out. Essentially, you can follow the formulas in the book, but the point is to try to understand how these are getting us back. So again, if you multiply this beta hat by the total, you're going to get an estimate of the total Y variable. If you multiply this beta hat by the X bar U, you're going to get a Y bar U estimate. So that is the idea here. So if the outcome variable is positively correlated with the auxiliary variable that you care about, then you would certainly expect that the ratio of sample means or totals, Y bar S over X bar S, is going to be less variable than you would get if you looked at the variation in the sample mean. Now, why do we care about the variability in the ratio? Well, if I have my Y bar S is equal to this, X bar U is a fixed quantity. That doesn't affect the variance. I'll pull it out as x bar u squared, right? That's sort of the formula. But what is really driving the variance of this estimator is how variable these beta hats are. Now let's take a minute and see why that is. So let's assume that you have this set up, your population. Here's the x variable, here's your y variable, and you do have this relationship, positive correlation between x bar u and y bar u. And you take a sample and you use that sample to estimate this line, you might get something that looks like that. And the x bar for that sample, if you project it up to the line, you're going to get the y bar sample, and the ratio of y bar s to x bar s is going to be approximately this true regression slope. And so in that case, you are going to see that every time that you do a sample and you estimate this true regression line, you're going to get something very close to this beta quantity. So these ratios, if you have a positive correlation between the two variables, you are going to get close to this b every single time. Now, when you take a simple random sample of y, you are going to be close to y bar u, but you might be up or down, etc. Remember that estimator, this is y bar u, and we might be close with any given one, but there's no relationship that governs how close we're going to be. The thing that will drive that is the sample size primarily. But in this case, the sample size is driving it, but also the underlying relationship between x and y is governed by this true regression relationship. And so that's what's going to drive or release or reduce the variability. Very much like what happens when we partition the sum of squares in stratification, we end up seeing that in an ANCOVA model, for example, you are essentially driving down the variability and getting a better estimator because you're taking away a portion of the uncertainty by using a covariate. And that's essentially what we're doing here. So the idea is that these should be less variable, but they could be biased. And we'll talk about that in a minute. And so we would take advantage of this correlation, and that should be what helps us. So let's talk a little bit about the means and totals. Again, so we've already gone through this here, and so I've explained this already, but this is really in writing, so I'm not going to belabor the point here. So let's look at an example, and then we'll talk through some of these things, and then we'll move on to the next segment. A simple random sample of neighborhoods is to be selected in order to estimate the average pregnancy rate among women per neighborhood in the population. This was a really important example that was motivated by some work that I did a couple of years ago on the National Children's Study, which was a heroic effort by the US government to follow children while they were in the fetus, while they were in vitro, up until they were 20 years of age across the country. Now, in order to recruit for this study, they had to know who was pregnant in a given block or who was likely to become pregnant so that they could actually take samples from the mother that referred to the baby in vitro. So in utero, I mean. So the point is that they needed a way to estimate the pregnancy rate and the likely pregnancy rate, the unacknowledged pregnancy rate that was going to be happening in these neighborhoods. So in this situation, we want to estimate the pregnancy rate. So every time you hear a rate, you should be thinking about a ratio estimator. So our outcome measure is the number of pregnant women in the neighborhood, and the X variable is the number of houses within each of the neighborhoods. And so essentially what we're looking for is number of pregnant women per household, which is the pregnancy rate. In other words, the proportion of households that have a woman in them that are pregnant. That's essentially what we're looking at. So the TY here represents the total number of pregnant women across all sampled neighborhoods. The TX represents the total number of houses across all sampled neighborhoods. And if I look at the total of Y divided by the total of X, it gives me the total number of pregnant women in our sample over the total number of households in the sample. And actually, this is not the sample. This is all sampled neighborhoods, essentially, because this is the population quantity. But essentially, this is the rate of pregnancy per household. X bar is the average number of houses per neighborhood. So remember, we're sampling neighborhoods, and then we'll sample folks in households within a neighborhood. And X bar just gives us the average neighborhood size with respect to households. And so this B times X bar represents the average number of pregnancies per household multiplied by the population average number of households per neighborhood. And that is essentially an estimate of the neighborhood pregnancy rate, or if you write it another way, the average number of pregnancies per neighborhood. Let's look at another example before we close out this segment. Suppose you wanted to estimate the total number of people who were exposed to an award-winning evidence-based injury prevention kiosk that has been placed inside of hospitals around the country. If you Google my name and the name Weaver, W-E-A-V-R, you will find that we had a study a couple of years ago in St. Louis where we actually looked at creating interventions for for parents of kids that were dealing with injuries for their children at home. So scratched arms, broken feet, cuts, wounds, etc. And so we actually created this intervention program that was released in these kiosks at waiting rooms around children's hospitals across the country. We looked at variables with a survey. We actually surveyed the hospitals, and we tried to understand why certain hospitals adopted our program and why they didn't. So you should Google Weaver Buskirk 2018, and you'll see that we have a paper on this. This example was motivated by that research that just happened a couple of years ago. So in this case, we could take a random sample of the population, and the Y variable represents whether a person was exposed to the intervention, and the X variable represents whether their hospital had the device in place. So this is an interesting thing because in this example, the X variable is a binary variable. It isn't a continuous variable. It's a 0-1 variable. And so what we're trying to do here is our B hat represents the ratio of the total patients exposed per adopting hospital. Because essentially what we're trying to get is an exposure rate, but exposure rates only refer to the areas that the exposure is present. And so in this case, if the kiosk isn't present, then obviously Y is going to be 0 there. So I'm going to have 0 over 0, and that's not going to work out. So essentially this is a way for me to get a better rate for looking at the total number of exposed divided by the total number of places that they could be exposed. So this T hat X represents the total of the number of hospitals adopting the program, and the product then of the B hat times the total estimates the total number of adoptees nationally. So this is again where we're looking at a Y bar total, for example. So that concludes our first segment on ratio estimation for Chapter 4. In the next segment, we're going to be looking through a couple of reasons why we should use ratio estimators and some justification around that, plus a few examples. So thanks a lot for joining me. Hope you all are well, and we will see you around for the next segment. Thanks.